Hello again. So this is expanding on, originally I had just put this in a slide in my Lustre presentation, but it turns out that there's been quite a number of improvements for ZFS, and wanted to break it out into a separate slide. And just as a caveat here, this presentation is focused on ZFS, but there's actually there's a whole presentation on LDiscFS improvements at LUG this year, and there's also many things going on in the ext4 and LDiscFS world, performance improvements and things like that. So don't feel like we're abandoning LDiscFS either. But this one's about ZFS, and so as you can see from the number of items here, there's these are just the significant features and improvements in the existing ZFS 0.7 release, which is the current stable release, and new features going in for ZFS 0.8. And obviously, in addition to this, there's many bug fixes and performance improvements and things that are not listed explicitly. So one of the things that's been a critical gap for Lustre deployment with ZFS is MMP, and for LDiscFS, it's multi-mount protection. The ZFS guys, they didn't want to use mount because you don't strictly mount a ZFS file system. You import it and the data sets. And so they called it multi-modifier protection. But the critical thing here is that MMP is a file system level mechanism for ensuring that two nodes in an HA configuration don't import the same pool at one time. And as bad as this can be for LDiscFS, if you have two servers writing to the same file system, at least with LDiscFS, the metadata is in fixed locations, the files are relatively static, so you get corruption, right? But, you don't get fatal corruption. In ZFS, if you have multiple nodes mounting the same file system at one time, it's basically, game over for ZFS, because it corrupts the pool in a way that is very difficult for it to recover, because it's writing this new metadata and they're overlapping and they all have valid checksums. They're being written correctly by two different nodes at the same time, and it doesn't have any way to repair the file system after it's corrupted. There's no ZFS check. And so based on the work that we've done for MMP on LDiscFS, this, we actually worked on a design for this many years ago at Sun, and Livermore took up the original design and improved it, and did the implementation, and did several improvements based on the fact that ZFS knows you have excuse me, multiple devices, and so it writes a label into each disk header that that indicates the devices in use. So it has a timestamp. Should I just get a drink quickly? So it writes a timestamp into each device header, and when the other node is trying to import the pool, it scans all of the devices for updated timestamps. It waits for a minute or a few seconds based on what update interval is being used on the pool, and then it rereads all of the devices. And so if it can detect that the devices have been updated, it won't import the pool. And so the good thing about this is that the overhead of reading all of the pools, or all of the devices in the pool, is only on the import node, and the node that currently owns the pool is only writing one header to each device. at a fairly rapid interval compared to LDiskFS, because there's multiple disk devices to spread the load. And if it's already writing an updated transaction, to the whole file system, it doesn't even write an MMP block, because the transaction update itself can already be detected on the importing node. And so this is only really causing overhead when the disk device is idle. And you don't add any significant overhead to the writing node. And so this is something that is enabled by default in ZFS, in Lustre 2.10 when you format a new file system. And it can be added to existing file systems if needed. Sorry. Okay. One of the other things that we had done for LDiskFS that is also important for performance in ZFS is being able to store the extended attributes close to the inode itself. And in the existing ZFS implementation, we had, D nodes are allocated in blocks, and the Lustre extended attributes were large enough that you always had to allocate a separate block for storing extended attributes. And because ZFS is mirrored, has ditto blocks for each bit of metadata, it actually allocates 2 blocks for each bit of metadata. And if you have 4K sector devices, which is common today, then you'd get 8K of extra data for each file that was being allocated. And so this actually consumed quite a bit of space and caused a high overhead in data being written. Sorry, my throat is failing me today. So then another feature written by Lawrence Livermore to have, essentially what happens is that, these are fixed size in the old form. These are 512 byte chunks of the file system, or sorry, of the metadnode file. And in the large dnode patch, it's allocating essentially contiguous slots in the same metadnode, so that you have multiples of 512 bytes to allocate extended attributes and things like that. And so the dnode size is not fixed like it is in inode size in LDiskFS, right? So you don't have to say 512 bytes inodes or 1K. Actually, in Lustre 2.10, because of progressive file layouts, we increased the default inode size to be 1K from 512 bytes. And with the ZFS implementation, you actually get a dynamic size. So as if we have more extended attributes that are being added to a file at creation time, then it will dynamically allocate a larger space for those. And of course, not only do you reduce the total space used because you don't have this external 4K block, but you also avoid the seek penalty for, even if it's not a seek penalty on an SSD device, you still have an extra I/O overhead that you're avoiding. And this is, again, it's a feature for newly formatted file systems. This will be enabled by default. You can use the dnode size equals auto to turn it on existing ZFS file systems after you've upgraded. It's worth mentioning, like any ZFS feature, once you enable it, you can't downgrade to an older version of ZFS and still mount the file system. So you'd only want to do this once your upgrade is known to be working. There was actually a fairly serious bug in ZFS 0.70 that the interaction between large dnodes and some of the improved allocation performance resulted in file system corruption. And unfortunately it affected one of the original founders of Lustre, Phil Schwann and his company, but they traced it down, and so that was one of the reasons for 0.7.1 to be released fairly quickly after 0.7.0, and so we don't recommend anybody use 0.7.0 with Lustre 2.10. One of the features that one of the Intel developers worked on is Inode Accounting, and this was partly driven by functionality reasons, but largely more driven by performance reasons. Lustre had implemented its own Inode Accounting. ZFS previously only did like space accounting, and it assumed you're creating inodes, they're dynamically allocated, they're allocating space, no different than a data block in a file. But people want to have separate inode accounting because inodes, lots of small files imply high ioperate, and so people want to be able to account for this separately. And so Lustre had worked on its own higher level implementation of inode accounting, but it didn't perform very well, and so moving the accounting into the same mechanism that ZFS uses itself allowed us to improve the performance, and it's actually something that other ZFS users wanted to have as well. And so, the native Inode Accounting was added, and it's also the template for we're working on project quota accounting, right? In addition to the Inode Accounting. I think I have a slide on that after. One of the big things that actually Adam will be presenting on later is the file create performance, and this took, this was a, sort of a drawn out year-long or year and a half of peeling the onion, right? We, we worked with Matt Ahrens from Delphix, who's one of the original ZFS authors, and we had to go through, what do we do, where's the current point of contention? Is it this lock? Is it, the amount of work we do for transactions? Single-threaded allocation happening in a certain place, or per CPU allocations, but they're all contending on the same lock, right? And so there's a whole bunch of different fixes, and only some of them are listed here, but dozens of different patches to improve the concurrent create performance, which is the staple of Lustre. But in many of the other ZFS workloads, it's a single server. You don't have many threads, or the databases, they pre-allocate files or stuff like that. They don't have a high demand in many of the ZFS workloads for concurrent create performance like Lustre does. And so this is just a listing of a few of the things. Having multi-threaded syncing of inodes after your transaction commits, or during transaction commit, I should say, it's writing it out, all of these updated, dnodes in memory. It can do that in parallel, right? Improving the object allocation itself, just the which dnode is being used next, was single threaded, right? It was like, okay, pick the next free number in this bitmap, and now you have per CPU allocation, so you get a chunk of dnode numbers, for each CPU, and yes, it results in semi, discontiguous allocation on disk, but usually if you have a heavy create workload, you're filling up those blocks anyways by the end of the transaction, right? So the concurrent allocation is helping significantly. Simple things like don't update, inode and block, quota accounting one block at a time every time you allocate a block. Now, instead of doing that, you just keep a counter in memory, and when the transaction commits, you say, oh, I allocated 1,000 blocks, or this user, allocated 1,000 blocks, right? And you do that once, and so it's fairly simple, but it was just nobody had really looked at optimizing these things in CFS, and so I'm not. There's a little quick graph here, but Adam has large detailed graph. I mean, basically you can see, you know, where we were a year or two ago. I mean, ZFS was getting, you know, 5 or 10,000 creates a second. Now in you know, with successive improvements, there's also improvements on the Lustre side for, you know, how efficiently we use transactions and things, and so it's manifold improvement. I think there's, yeah, it says here there's the description of the hardware, test hardware is at the end, but significant improvements here. Another interesting thing that that we're working on with another group inside Intel was it's QAT Hardware. It's a quick assist technology. It's essentially you know, a chipset that you know, one of the functionalities is hardware crypto, right? But another functionality that is in there now is gzip compression, and so you could do the offload of the compression to another chip instead of using CPU cycles. And what's interesting is we can now get, you know, hardware-assisted gzip compression that's running, you know, not only not using CPU cycles, but it's running much faster than the CPU, and you know, giving you much better compression than you know, LZ4. And you know, this is something that's ZFS is already doing compression for all metadata by default, but you can also do, you know, this makes it possible to do data compression. These are numbers just at the ZFS level, not at the Lustre level, but the graph. But, you know, equivalent performance could be had on the server side. One of the tricky things right now, though, is that this is an add-in PCI card, or it's in the I can't remember, North Bridge or South Bridge in the separate chipset, and so it's currently, it uses up PCI lanes, and so on OSTs, you know, those are precious commodity for you want to have lots of network and disk bandwidth. So it's not for every workload, but in some workloads where you have you know, a high benefit from data compression, you know, this might make sense. This is just a quick graph. It shows you know, the you know, this is the CPU based you know, for software compression, and you know, I think this is LZ4 software compression, so this is a much lower CPU usage, but from the previous graph you get, you know, half or less of the compression ratio. And these ones, which one? Black and green, this is the CPU usage when you're doing gzip compression, you know, with the offload, and so it's you know, doesn't hurt the performance very much. One of the other projects, like a big project that Intel has been working on, is Coral, which is one of the big Department of Energy in the U.S. You know, pre-exascale kind of systems, and they've been working on a number of different features for ZFS for the Coral project, and one of them is fault management architecture. And if you are familiar with Solaris, FMA is you know, sort of a core engine. It does things like correlate all kinds of different events, you know, so that you don't get let's say error messages from you know, a NIC failing, and then, you know, the TCP level error message and a whole bunch of things, you know, flooding your consoles and stuff. So FMA kind of integrates a bunch of different events and says, okay, I know that this is a disk failure, or I know that this is a, you know, a path failure, rather than, you know, the disk when I got this IO error, right, based on a whole bunch of different things. So it can do correlations, and this has been ported to, FMA has been ported over to ZFS. And so, you know, right now it's only doing correlation of IO errors and checksum errors and things like that, and it's used to drive the ZFS event daemon, which is like a daemon in user space for handling disk faults, and or taking, you know, disks with repeated checksum errors, you know, and saying, okay, after, you hit 1,000 checksum errors on this disk, consider it failed and, bring in the hot spare or something like that, right? So you can write rules and things in FMA and automate the, disk replacement. I mean, it's one of the things that was with ZFS on Linux up until recently, doing the disk management it was mostly done by hand. It also, allows what I like to call blinking lights, which is this is something that Livermore did, is hooking ZFS into the SCSI enclosure services from Linux, so that you can, say, okay, this disk is faulted, and illuminate the light on the disk, right? And so SES is sort of a generic infrastructure that works with a whole bunch of different enclosures, so you don't have to, program your own scripts to, work with, vendor A versus vendor B versus vendor C, disk enclosure, right? This is a standard library for managing the blinking lights. Another big feature that was worked on for Coral is declustered parity RAID. And so one of the big, issues with any RAID system is the rebuild speed. And so declustered parity RAID allows you to use, the performance of all of the disks in your system to do RAID rebuilding. And then instead of having a dedicated hot spare device, it distributes the spare space around all of the different disks. And not only does that allow you to rebuild more quickly, but during normal operation, you're not having, 2 out of, 20 or 30 disks just sitting there idle waiting for another disk to fail. You're able to use the IOPS and the bandwidth and things of those spare disks, during normal operation. And there's a slide here. So, for different chunks of the disk, there's pseudo-random distribution of disks, in each group. So this, first thing, 4 disks plus 1 is just an example. It can be any kind of geometry. But you have 4 data and 1 parity, and then another 4 data and 1 parity, and 2 spare, chunks. And the ordering of these disks within any parity redundancy group and the spares is generated with pseudo-randomly, and then the pattern is repeated for a period, so that you don't have to generate thousands of pseudo-random numbers. But for different regions of the disk, the pseudo-random distribution of disks is different, so that if any single disk fails, those failed regions are in different parts of the parity, and they have different peers, right? So if disk 5 fails here, you'd be rebuilding against 4, 3, and 10. And this one, you'd be 4, 6, and 11. Here, if disk 5 fails, you're building against 2, 3, and 10. So you're able to use all of the bandwidth for both reading and for writing to do the rebuild. Another, in a way not surprising need in ZFS is, this is metadata isolation. It's essentially Lustre in a box, right? So you have separation of data and metadata within one file system, right? And, because of different workload characteristics for metadata, small blocks, high IOPS, right? Data is large blocks, is, largely streaming, reads and writes. You want mirroring for the small ones. You need RAID Z for the big ones. And so metadata allocation class is the implementation of separating ZFS metadata. Either you can do it in one of 2 ways. One is you have a dedicated mirror device that's, you could put it on SSDs, right? It's a separate VDEV that has, a mirror policy versus RAID Z. We also added it, combined it with the D-RAID, so that if you have a very large VDEV, you can dedicate some regions of the disk to be mirrored versus other regions of the disk to be, 1 or 2 or 3 parities. And so all of the small blocks are allocated together versus large blocks being allocated in a different part of the disk. And this is just symbolic. The mirrored regions, are spread through the disk to give you avoiding seeking. And this gives a good improvement in performance. There's a number of other miscellaneous improvements. One of them, this is actually sort of a Lustre improvement. It's OI scrub for ZFS, and while in theory ZFS never gets corrupted and has checksums, there are software bugs or other regions why the Lustre object index might become broken. Or if one of the other issues is a backup and restore. If you did a file level backup and restore, ZFS has sort of a low level backup and restore called send and receive, and that maintains all of the metadata exactly, even if you send it to a different layout of disk. But if you do like a tar or an rsync, or if you want to migrate from LDiskFS to ZFS, you can do like a tar or rsync backup from LDiskFS into a ZFS file system and run OI scrub, and then it will rebuild the object index because all of your inode numbers have changed. And so that's a Lustre level feature. The ZFS on-disk encryption is something that landed for, this is incorrect, I'll have to fix this. It's actually landed for ZFS 0.8. And it's software encryption. It hooks into hardware acceleration if it's available, but it does, because ZFS is tree-based, it has a per block encryption keys that are maintained, and but currently there's no Lustre level integration for this, so you'd have to have some external tool that's managing the keys for unlocking the pool at mount time. The project accounting for ZFS to match the LDiskFS equivalent feature, and improving the scrub and resilver speed, which works. This is to improve RAID rebuilding for ZFS, in the absence of D-RAID, to do ordered I/O. And so I think this is the last slide. So ZFS has been updated in Lustre 2.10.1 and 2.11. The goal is that ZFS 0.8 will get these features, metadata allocation class and D-RAID, more quickly than ZFS has been released in the past. I mean, as it showed here, I looked back, took over 4 years between the release of 0.6 and 0.7 for ZFS. We're hoping 0.8 doesn't take that long, and we've had some discussions with Brian, and that's happening. And there's a bunch of other improvements, but I was focusing on the ones that are related to Lustre, right? And I think here's the hardware, and that's it. I have
Thank you.
One question, I don't know, or less.
Yeah, we can take one question. No question?
Behind you.
One kind of odd one. Why is it multi-modifier protection and not multi-mount protection like I thought it was on LDiskFS? Question.
Yeah, I explained that.
Oh, sorry, I missed that.
They just don't like saying you don't really mount ZFS,
Okay.
right? Because you import the pool and then all of the data sets inside or mount themselves, right?
Sorry.
And that's how they are. I don't know. All right, thank you.
Okay, thank you.